Good afternoon, everyone, and welcome to this very special Charles Edison Lecture, which is hosted by the College of Engineering at the University of Notre Dame. My name is Patricia Culligan, and as the Dean of the College of Engineering at Notre Dame, it is my pleasure to open this event, which features a lecture by one of our very own distinguished College of Engineering alumni. Engineering classes were first offered at Notre Dame in 1873, which means that we are celebrating 150 years of engineering at Notre Dame this year. This places us among the oldest engineering programs in the United States, and we are the first Catholic university to introduce a formal engineering program. In 1873, which was only 31 years after Notre Dame was founded, the university announced a formal program in civil engineering based on the technical needs of the United States at the time, which included needs for surveyors and the designers of railroads, roads, and bridges. Throughout our history, Notre Dame Engineering has continued to focus on educating skilled leaders and innovators who can serve the needs of society at the time and to advancing knowledge and promoting discovery to support a better world for all. The Edison Lecture Series in the College of Engineering was established by Paul Christensen, president of the Charles Edison Fund in 1989, and it is our most distinguished lecture series. The lecture series centers on topics arising from research in science and technology with the goal of stimulating interest in, as well as encouraging participation in STEM innovation. This Charles Edison Lecture is our college's capstone event, celebrating 150 years of engineering at Notre Dame, and I personally could not be more excited and more grateful that Professor Newman of MIT agreed to deliver it. I would now like to welcome to the podium Professor John McGreevy, Notre Dame's Charles and Jill Fisher Provost, to introduce our distinguished speaker.
Welcome. What a great day this is. Thanks to Dean Patricia Culligan and the College of Engineering, and to you for attending what will be a marvelous lecture. As Patricia said, we're celebrating 150 years of engineering at Notre Dame, and it's fascinating to look back on the achievements that have been made over that century and a half and imagine together what we might accomplish in the next 150 years. Joining us today to think about those next 150 years and to celebrate this milestone is an extraordinarily accomplished alumna, a fellow member, I will add, of the class of 1986 from Notre Dame, Professor David Newman. Dr. Newman is currently the Apollo Program Professor of Aeronautics at MIT, Director of the MIT Media Lab, and a faculty member at Harvard-MIT Health Sciences and Technology, a program that trains MDs but also trains them as engineers, hoping to create the next generation of physician scientists. From 2015 to 2017, Professor Newman was NASA's Deputy Administrator, becoming only the third woman and the first female engineer to serve in this role. Together with the NASA Administrator, Dr. Newman was responsible for the agency's vision, leadership, and policy direction, and she also represented NASA to the White House, Congress, international space agencies, and industry. She worked in Washington to craft a large-scale strategic framework to implement best practices for the agency and form new partnerships to develop spacecraft. Thanks to her efforts, NASA became the best place to work in the U.S. federal government during each year of her appointment, and she was awarded the NASA Distinguished Service Medal for her work at the agency. Dr. Newman's research focuses on the intersection of aerospace and biomedical engineering. She uses innovative techniques to investigate human performance across the spectrum of gravity, including spacesuits, life support, and astronaut performance. She developed the BioSuit, a supple second skin spacesuit that allows astronauts greater flexibility while also providing the pressure needed to function well in a low-gravity environment. Time magazine called this suit one of the best inventions of 2007. Dr. Newman once set a world record for women's human-powered hydrofoil speed. She once circumvented the Earth in a sailboat. She has championed the idea of humans journeying to Mars. She's exhibited her inventions not just in the STEM arena, where you might expect, but in art museums around the world, including the Victoria and Albert Museum in London, the Metropolitan Museum of Art in New York, and the Venice Biennale. She's inspired many women to pursue careers in STEM and design. And I don't think this is the most important accomplishment. On International Women's Day in 2019, Mattel honored her with Astronaut Barbie as part of their Barbie Scientist series. The doll was even wearing her own Barbie biosuit. So Dr. Newman embodies the idea of being a force for good in the world. In an interview for a feature story done with Notre Dame Magazine a few years ago, she said, "Any technology we build, we have to ask, how can we serve people? That has to be the center of our work as engineers, and that's something that was instilled in me at Notre Dame." How proud we are of that statement and of the professional life that has underlied it. Thank you, Professor Newman, for inspiring all of us. Please join me in giving a warm Notre Dame welcome to Professor Dava Newman back to her alma mater for this Edison Lecture in celebration of 150 years of engineering at Notre Dame.
Thank you. Thank you so much. Thank you. Thank you for that very fine, wonderful introduction. I'm so glad to be back. How's everyone doing? All right, let's take a journey. Just my honor to be with you in to celebrate 150 years of great engineering. So, in all of exploration, we have three fundamental questions. They're big, bold questions. Are we alone in the universe? Are there other habitable planets? And is there life, meaning is there life elsewhere? The evidence is mounting. Big prediction. I think we'll find life probably in this coming decade. In the 10 seconds that you've been watching this amazing view from our Hubble Space Telescope, 3,000 new stars were formed. So that's the world that I live in, the magical, the awe-inspiring, the infinite. To kind of look and be an explorer and see if we can make some headway on these big framing questions. Did you hear about our James Webb Space Telescope? Yeah, it's rocking it. Every day I take a look and see what's happening, what new galaxies, clusters, what are we finding? And again, what about the out there? All of this I like to put in the context of, this is not an eye chart, but to just take you, not just the solar system, but beyond. So Earth, I have to point out, is a pretty small blue pale dot right there. That's our pale dot. So put it in context. This is in astronomical units. Mars, our sister planet, we're going to talk about. But we're sending our technology. We're sending our probes. We've already gone through the solar system. There's Voyager 1 and Voyager 2, still sending back scientific data to us. So this is the world of not just aerospace engineering, but astrophysics, all science and engineering, where we come together to explore, to answer those three fundamental questions. I'm going to zoom in a little bit closer to home. This is my comfort zone. So you see our Discover camera taking literally a picture of Earth and the moon. Now, Mars is half the size of Earth. The NASA mission Discover, with this epic camera looking at, I call it the solar system weather buoy. Why? Because here's Earth, here's spaceship Earth, here's Earth, and here's the sun. And guess what? That mission, that scientific mission, is out there. It's Lagrangian point 1. It's 1 million miles away, and it's looking at Earth, saying, hey, Earth, here comes your space weather. It's monitoring and measuring. Here comes the solar wind, the solar radiation. So it's out there exploring and telling us all about atmospheres, but our space atmosphere, our solar system atmosphere. So my talk, I'm going to kind of zoom in, tell you a little bit about what we're doing for the next step, and that's getting humans back to the moon, what we're doing on Mars, my second favorite planet, and Earth, my very favorite planet by far. And we'll come full circle and come to Earth and talk a little bit about what we're doing with technologies to observe Earth to end the talk. There's some sound on here. Hopefully we can have that. Oh, can we have the sound on here? I'm going to have to pretend I'm Jack Schmidt. It says, uh-oh, it fell. This is the last time we had humans on the moon. This is Apollo 17. We sent a scientist. We sent one scientist to the moon. That was Jack Schmidt. We sent a geologist. I call them my Apollo bloopers, right? Pretty hard to explore, really hard to do science in that suit. But that was pretty incredible for 1960s technology. So the spacesuit is it's an amazing engineering feat. It's like taking a spacecraft and shrinking it around the human body. You have to provide all of the life support systems, your oxygen, scrub out your carbon dioxide, provide and keep the astronauts safe and healthy and well and alive. Over to the right, you see a schematic of the current spacesuit. We've used it for the space shuttle era. We're still using it with just small incremental changes for the International Space Station. So it's an engineering marvel, but very old technology. It's not the only way to design a suit, in my opinion. Again, an engineering marvel, but why would you take a 160 kilo can, it's almost 300-pound suit, and shrink it around a person? It's not very mobile. It's very hard to move. You're making our astronauts, which I train astronauts, all my students want to be astronauts, we're wasting all your energy just to move against the suit, right? I want them to find life. We're going to the moon and Mars. We have to be agile, kind of like Notre Dame athlete type of explorers and astronauts. So that's what I think about a lot in some of my research. And NASA, I'll put this framework up, but sometimes it's useful. I developed an innovation framework. It's a very large government agency. Guess what, all the new hires, they're all of our students. They're super innovative. They go to NASA, they want to innovate, and the administrator and myself, we sent the emails, thou shalt innovate, be innovative. But there's the middle. And so I have to thaw the permafrost. 15,000 people, they didn't get the memo, right? How do we make everyone innovative? So I put this framework together. I think everyone can be innovative at universities, at government, and industry, of course. So real quickly, on the bottom, I call that continuous innovation. That's 80% of innovation. Just go to work every day and be excellent. That's really where innovation comes from. Then we break it down over to your right. I call that revolutionary innovation. And that's new technology. That's a technology push, revolutionary technology, no new business model, no new organization change for your business. So that's where I live. That's my sweet spot. Over to the right in red, call that disruptive innovation. That is a new business model. No new technology, that's a business model. That's where some other folks live that we'll talk about. And if we're really smart, we do them in parallel. We do our technology and our business model or organization change. So I call that transformative technology right up at the top, and that's really tough, but I think we can do it. So a little bit about technology and some of the things that I get to work on as a researcher is, that didn't look like the suits I just showed you. It's not 160 kilos. As a matter of fact, our design goals are 20 to 40 kilos for an entire spacesuit. We take the human body, I design it from the inside out. I take human body, human performance, and we say, now what kind of system can I put on top, a second skin system, literally on top of a human, to empower them, to make sure that they can find life, say, when we look for past life on Mars, as we're doing today. So a little bit about the technology and the engineering that goes into that. We map you in 3 dimensions. So laser scans, definitely see people moving there. That's a digital image correlation. Taking a look at movement. I want to give everyone as much movement as possible. Up on the top right, you see a circle, blue circle, turning into an ellipse as you move, right? So there's only one pair of those red bisecting diameters moving from the circle to the ellipse. Now they pivoted, but they did not extend. So I call those the lines of non-extension. And then with some 3-dimensional eigenvector math, voila, you have a Spider-Man looking suit. So we map strains and stresses, streamlines, all kinds of things that I learned here in engineering, but I just apply it to humans. And the human body is very complicated. And again, trying to design this skin-tight suit, a lot of materials development as well. So where we're at today, I've been working on this for a while. It seemed like a really crazy idea almost 15 years ago, but NASA bet on us and said we'd take some crazy ideas. And I said, yeah, I can shrink wrap my astronauts. Let's just try. So the real hard, or like dip them into a paint bucket. That was the initial. And I even put in, I need to study giraffes in that proposal. The only NASA proposal I ever wrote that said I need to study giraffes. We were sailing our boat around the world, and I really wanted to study giraffes. And I'm pretty sure they have an automatic G suit in because, they don't faint, right? 5-meter tall animal, they're chewing the leaves, they bend down. We hop out of bed in the morning and we almost faint. I'm like, what is it about giraffe design? So I get to study giraffes. Okay, back to the biosuit. Has some of that technology in it. The challenges are, you have to compress. I need to apply 1/3 of an atmosphere. It's just under 30 kilopascals of pressure, constant pressure to keep you alive in a vacuum, right? So first it's a pressure suit. And you want to be able to, get dressed quickly. So I need to don and doffing, we call that in spacesuit terminology. You need to put it on, and you have to put it on by yourself because you don't have a lot of partners out there in space, and we can't waste astronaut time. So the really needs, compression technology. It's all about mobility. We have to invent new materials, advanced materials that can sense. And I'll show you a little bit of our latest prototypes that we're working on right now. This is a video that's going to go over, and I'll just narrate it as it goes. So we're inventing some new fibers, specifically sensing fibers, so that we can track kinematics, track your motions as you go, and also measure the pressure. How much pressure is my suit providing? Is it providing that 1/3 of an atmosphere, that 30 kilopascals that we need? Humans are very complicated in terms of a shape. So that's where the 3D scanning comes in. You need to have a very, very interesting shape, especially if you want full flexion and extension. And then we invent these fibers. We need to put them into the textiles themselves. And as I said, these fibers are measuring your kinematics, how much you're bending your angles. And then this one is telling, okay, how tight is the suit? Is the suit tight enough for the real extreme environment of space or a vacuum in space or for moon next stop? You put your little computer there by your hand there, and donning and doffing. And can I put it on? So it has a two system, a zipper system, as well as kind of cinching it up. And that cinching uses some shape memory alloys, some advanced materials, alloys. That's how we get the kind of fine tuning, if you will, of the compression or the pressure around your arm. So far, so good. We will become interplanetary. People are going next to the moon. I hope we don't get stuck on the moon for too long, because we need to get people to Mars, because scientifically, so valuable to go find the evidence of life, past life. Talk a little bit more about that. Did want to talk quickly about the recent mission we were on. That was this summer. It was called the Axiom, the AX-2 mission. Private astronaut mission. Who would have thought? Thought it was the domain of governments and world space agencies. But we kind of changed that paradigm. We said, no, public-private partnerships are the thing of the future for NASA. And it's taken a decade. Companies are rocketing it, like SpaceX, and flew 3 paying customers, and then Peggy Whitson, the commander, who's the most decorated and longest-serving astronaut we've ever had. So she didn't have to pay, because everyone wants Peggy on the mission, because she really needs to train all the rest of the astronauts. So we flew a suit. This is the versions of, we call a skin suit. Now, this isn't to keep you alive outside the craft. This is inside. This is your exercise suit. So when you're intravehicular activity, when you're inside, you potentially lose a lot of muscle and bone, and even you get longer. That would have been great when I was a basketball player here, because you can see I'm challenged. I always wanted to slam dunk, and I could never. But my suit compresses you to get rid of back pain, because that's a real issue for our astronauts. And you might lose 30, 40% actually muscle atrophy. So you have to exercise a lot. That's the good news. You might lose 1 to 2% bone mineral density per month. Now who's going on my 4-year Mars mission? Come on, the students still usually want to go, right? But as you get aging, and from when you're 50 years old to 60 years old, you might lose 1% bone mineral density. Well, it's the world's best, laboratory up in space. This is on International Space Station, because we can test that, in each month. That's why you have to do a lot of exercise. You always have to do exercise when you're in space because we don't want the astronauts to lose much musculoskeletal decline. So we fly these suits, but for the first time we got to fly it on private astronaut. It was only took us 8 months, and my PhD student could run the whole mission. It used to take me 10 years to be the PI for an experiment that would maybe fly into space. So it's a new ballgame. This is disruptive innovation. We can move really quickly. It's much cheaper, and I think it's a win-win for private companies as well as the government and as well as academics who want to fly our experiments in space. So here's the private astronaut. I call him a rookie because the first time in space and got to spend 10 days there. You do move really slow. This is actually real time. These are real time videos. Might surprise you how slowly we move. Again, you're trying to become that Olympic athlete. You're trying to make sure that your musculoskeletal control is there something up with my.
You keep talking. I'm sorry.
Okay, I'll keep talking. Because I can talk over them. So exercising in space while wearing a leotard, but we have a beautiful name for it. It's called the Gravity Loading Countermeasure Suit, or just skin suit for short. And we're glad to fly it. We've flown it on European astronauts as well. Let's just see, I think. All right, let's go from, again, on a space station. Let's go to Mars where I spend a lot of time. I don't know. I wake up every day and see what the temperature in Mars is. How about you? A little bit colder today on Mars than it was in Chicago and South Bend, but not much. We get to freezing on Mars. So how many people saw the movie Martian? All right. Who would have known that would have been a bestseller? We had no idea. We're nerds, we're at NASA, and Ridley Scott just made a great movie, and Andy wrote a great book. But what a treat to be there with that during that time. And but it won't all be potatoes. I'm just telling you, they got 3 things wrong technically, and I'm glad to take that in Q&A. Only 3 things wrong. It's an awesome movie. It's great. Well, we're the real Martians. We actually are doing experiments on Mars today. I'll tell you about MOXIE, which is the MIT experiment. Just want to celebrate, again, this is the latest mission is our Perseverance rover. And that little helicopter, let's look at that little helicopter, and maybe you'll hear some sound. No, we're not hearing the sound here. I'll have to, we can do that. Well, there's people cheering and screaming. That's a very small helicopter. It's 1.5 kilos. That's all we had. And guess what? Everyone said, no. We have Perseverance, rover. We are not having a helicopter. I said, no. I knew there was sound. on my videos. We tested this before we came out. See, Murphy. Maybe it's because I'm at Notre Dame. Murphy, special name here. So maybe that's why Murphy took away our sound, but that's okay. It's just to excite you and make sure you're still with me and waking up. And I show that because it's all about the people. It's great. So there's some other sound coming up. There's a lot of sound, but I would like you to hear some of the sound coming up. But it's all about the people, right? The designers, the people. And it's also about innovation and getting to yes. Because everyone told me, no, we can't fly that new technology. How many Mars missions do we have? It's a $3 billion mission, it's serious business, right? It's only a $50 million helicopter. Okay, it cost $80 million, not too big of an overrun. And we didn't have any room for it. So guess what? She's built it right on the underbelly there. That's where ingenuity lives. Why? Not because it's elegant. We had no room for it. I said, I'm flying this thing, and we're going to do it. Because guess what? Now she's the star of the show, right? Because you're going to go explore and look for life on another planet. I want to be in 3 dimensions. I am an aerospace engineer. So it just didn't make sense not to fly. Now, all the future Mars missions, guess what? We have rovers, we have helicopters, we have, 3-dimensional flight. It's just a way that you explore and you get much more science out of your mission. I want to show you what we're doing with augmented reality and virtual reality. We've changed science. There's 30 principal investigators on this mission, and they're all over the world. So their 8 a.m. telecon is with augmented reality, and you just beam your avatar up to Mars. You might know, we're in Jezero. We're in the Jezero area looking for past evidence of life. Earth and Mars, 4.5 billion years old. 3.5 billion years ago, Mars lost its dynamo. You don't want to lose your dynamo. But That's just electromagnetism and its spin. So the solar wind and solar radiation now leave us with the Mars we have today, which has a 1% carbon dioxide atmosphere. But Mars could have been wet, wonderful, wild. It's a sister planet 3.5 billion years ago. So we think that the life we'll find initially will be past life, very old, but it has all of the chemistry, it has all of the signs for life on Mars that life could have existed. So that's why we're there, that's why we're in dry lake beds, that's why we're taking samples on this mission, caching them. Now we need the next mission to go get those samples and bring them back to Earth. But we've already revolutionized science because now you are at Mars with the HoloLens on. And why is that so important? Because now you're not a single, PI scientist. No, geologists, which I am not a geologist, they all look like rocks to me, right? No. Any geologists there? Boy, they fight all morning about rocks. And since I can only take 5 images, 1, 2, 3, 4, 5, let's take the best images. Let's take the ones that are going to be the scientific breakthroughs. So it's worth it to transport people to these extreme environments that we're exploring. And it's a lot of fun. But I think we've proven, that we get better science done if we fly our technologies, complementary. So if we still have sound going, I think we do. It's soft, and there's a reason it's soft. That's the sound. These are some of the first sound recordings ever recorded from Mars, brought to you. This is the laser. Tap, tap, tap. We're blasting rocks, trying to look inside the rocks, seeing if those fossils are there. It's always windy on Mars, that is true. So 1% carbon dioxide atmosphere, say. So it's a light wind, it feels like a feather, but always windy. And it helps, it blows off some of the dust from our solar panels. 1% carbon dioxide atmosphere compared to our atmosphere here. So that's why these are so soft. I'm gonna share a recording, an ocean recording here on Earth, and it's the same recording, the same audio, the sonogram, and it'll be filtered to tell you how it would sound on Mars. So it's quite a bit difference. You hear the basses. You just hear the basses. All the high frequencies are kind of filtered out. And the schematic, that's the MIT experiment we have, MOXIE, Mars Oxygen In Situ Resource Utilization Experiment. Say that twice. It's also a drink, from the 1800s. We named it after a carbonated beverage. We are taking that carbon dioxide atmosphere. Basically, you split the carbon atoms, and you have CO, you leave carbon monoxide, and then I have oxygen left. So we're literally making oxygen. We're taking oxygen out of the atmosphere of Mars into it's kind of a reverse fuel exchange system is the way to think about that. MOXIE right there, but it's pretty fundamental. It's pretty breakthrough. Of course, we need to scale it up. We have an hour run, and we can make about 10 grams of oxygen. Now, you might think it's for my humans in the spacesuits. That's secondary. First, we need to make fuel. For a round-trip mission to Mars, you'd really love to have your fuel depot there with all of your fuel there to fire up, the craft to come back home. It is a round-trip mission, no one-way missions. That wouldn't be ethical, and it wouldn't even be interesting. Everyone wants to come home. And then the final audiogram I want to share with you. Let me see. I think this one plays. Yeah. Hopefully. Nope. Well, sorry about that. We're having some audio files. You have to jump on. It's all open source. These are all available to you. A meteor just hit Mars. And it's the first time we've ever recorded a meteor hit on another planet. So it's right there. And it goes bloop, bloop. And I was like, whoa. And it has to do with it coming in the atmosphere. But it's pretty interesting because, again, I want to play with all the senses, give this information to everyone. These are all open source to make sure that we can share all this data with the world. That's what we intend to do. We will become interplanetary, not that it's option B, it's for scientific discovery, is to make us hopefully live better on this planet. But I think we are gonna have a lot of fun, especially if we get to send one of my biosuits. You get to the moon, you get to do you jump 4 to 5 times your height, so then I can definitely slam dunk on the moon. Mars, I can only jump 3 times my height, but still, no problem. So it's really exciting. It's really exciting times with the technology and the science and this incredible age of discovery that we're in right now. I couldn't be happier. So now I want to take us down to Earth. And I'm at the Media Lab at MIT. If you're wondering what that is, it's this crazy, wonderful, magical place. And I still am the Apollo program professor, and we're still, doing work on space. But now I also get to interact with a lot of artists and designers, as well as scientists and engineers. It really is a multi and transdisciplinary place. I've been there the last couple of years. We've done some strategic foresighting to think about what we want to do in the coming decade. Actually, the question we asked to our stakeholders was, in 20 years from now, what are the most important challenges for humanity? That's what we have to focus on. What impact can we have for society? So we asked 20 years out, and then we backed it down for 10 years and said, okay, where do we have expertise? What are the biggest challenges that we can work on? And maybe not surprising, guess what came up? Climate. So I call that Future Worlds. It's pervasive, life with AI. Well, I'm actually going to show you a Gen AI, because you can't have a talk now without Gen AI, right? That's just the world we live in. So I'm going to show you myself from 2050 to talk about these 5 areas. And I hope we have sound on this. Great.
Hello, everybody. I'm Future Deva, beaming back to you from 2050. I'm very happy to finally see you. The early 21st century was a fascinating era in Earth's technological history. Historical evidence suggests that the Media Lab was at the epicenter of the broader solar punk shift of the century, where many exciting trends coalesced into this hopeful 2050 I live in. One of the most significant shifts started with inspiring real action to create a more sustainable and equitable world. The Media Lab played a crucial role in catalyzing this change by fostering interdisciplinary research and collaboration across fields. Here are the 5 themes we really started to revolutionize back in 2023. Life with AI. The Media Lab explored coexistence with intelligent systems, placing humans at the center. The lab developed ethical guidelines ensuring fair, transparent, and accountable AI design. This fostered a harmonious relationship between humans and AI, an essential tool for complex problem solving and enhancing our lives. Decentralized society. The Media Lab promoted a decentralized society, distributing power and decision-making among the people. This involved exploring alternative systems of governance, finance, and communication, creating more democratic and resilient structures, reducing inequalities, and fostering trust, collaboration, and community. Future Worlds, the Media Lab's research on climate helped build a sustainable and inclusive planet, pioneering new materials and urban planning strategies to mitigate climate change. Nature and technology were integrated, creating a harmonious coexistence between humans and the environment in the oceans, land, and space. Cultivating creativity, the Media Lab nurtured creativity and innovation globally, leading to groundbreaking discoveries. People from diverse backgrounds collaborated to create solutions for global issues through experimentation, risk-taking, and pushing boundaries. Connected mind and body, the Media Lab's research on the mind-body connection revolutionized well-being, developing personalized therapies and mindfulness practices that enhanced mental health and cognitive abilities. Technology and science were integrated to significantly improve people's lives, and cyborg mobility was realized. So we should get started. There's lots to do.
So there is lots to do, absolutely, and we're pretty focused on these. We think that those are 5 really important areas for us that, again, bridge across so many different areas. So again, Life with AI, these are some of the areas that we're really pursuing research in, but again, it goes from the technology all the way down to the policy and the law, across engineering, across science. For Future Worlds, that's the design and action for that future we want to live in. And so I'd like to highlight a little bit of research in this area. So I tend to work, actually, probably 60% of my research now is for climate, and only about 40% is actually in space because of the urgency. So I'll highlight a couple things we're doing, which I call changing the conversation. We're changing the conversation to talk about the dual challenge of energy and climate. The world needs affordable, cheap energy. That's just factual. And then how do we have all of the energy, the fossil fuel producers, natural gas producers, the renewable producers at the table with the climate folks. We have COP28 going right now. And if we get everyone around the table, I'm sure we can have much better win-win discussions and move forward. That's how we can accelerate positive change. So I want to show you just a little bit of our work there. And then kind of a crazy idea, but I also want to design, and we're working on to build a mission control for Earth. Because did you notice Earth didn't come with an operating manual? And maybe that's what we got wrong. So if we could just have an operating manual for Spaceship Earth, maybe we'd be able to help a little bit more. So this is the data I have. Actually, I have 100 terabytes a day. That's a lot of data. A lot of data. I'm drowning in data. I have a lot of data from our Earth observing satellites. Now, this is the NASA constellation. We have a European constellation, and we have a lot of private satellites looking down on Earth. So eyes on Earth. We take all that data, we monitor, we measure, and I look at Earth systems. I start at the ocean system, tell you temperature, tell you about how things are changing, biodiversity in the oceans, moving to the land, precipitation, look at agriculture, look at precipitation. All these I call the vital signs of Earth and all of Earth's subsystems from oceans, land, air, and going all the way into space. And you'll see, I think you see. There we go. This is carbon dioxide. I want to talk to you about carbon dioxide. I'll come back to carbon dioxide in a minute. This is just a preview, a holistic view of the Earth, because we're all global citizens and we're all astronauts. We're all crew on Spaceship Earth. And this is CO2, emitted greenhouse gas. You see this flashing green. That's good news. That's an everyday cycle of absorbing the carbon. The Amazon is doing its job. The oceans are doing their job. Now we have to ask people to do our job. So I want to share a few more of these vital signs with you. Again, this is our data. What this is the world's history of temperature data from 1880 to present day. Blue is 1 to 2 degrees below an average 30-year mean. Yellow and orange are 1 to 2 degrees Celsius, or 2 to 4 degrees Fahrenheit, if you think in Fahrenheit, above a 30-year average. So raise your hand when you're born, 1980s, there you go, 1990s, 2000s, thank you, class participation points. It's hot. It's really hot. Same data, starting from the 60s, way back when I was born. Okay, you're taking a look. Again, 30-year running average from 1950 to 1980, and this is the anomaly, 1 to approaching 2 degrees hotter. We're at 1.17 today. I don't even talk about meeting the climate goals of 1.5. We've blown right past them. I do talk about meeting climate goals for 2 degrees Celsius, because that is still within our power, 6 years and counting. Let's take a look at carbon dioxide, one of the emitted greenhouse gas, as well as methane and other things. So this is a year in the carbon cycle. It's from 2014. To orient you, blue is good. Blue is below 400 parts per million. Yellow and orange is above 400 parts per million. We don't want to be above 400 parts per million. And I show it in 3 dimensions, 5, 10, 15, 20 kilometers up. This is literally the definition of a trapped greenhouse gas. It's from humans and all of our emissions, and it's also from natural disasters and fires. So that's the emissions. We can change this. So this is not doom and gloom. I'm just showing you the data. It's completely within our power to change our own behavior at the individual level, to change regional, to change policies. We have to change everything. This is a complex system. All of weather, climate is a complex system. But I'm very optimistic. We just have to have the will to change. I'll be spending actually Christmas and New Year's, can't wait, in Antarctica. A little colder than here, not too much. And I'll be flying a drone, and I'll be taking camera images of the peninsula. I've been to McMurdo, the U.S. base, as well as the South Pole. That's me on the South Pole. We sailed our boat around the world, took 18 months, going 6 knots, and all you have to do in Antarctica is go like 2 seconds. But I did get, you frostbite your finger. You got to put your gloves right back on. And iPhones, they freeze. I went through 2 of them. Thank goodness we had another person with a camera around. Cold. Antarctica, the day I was there in summer, was 30 below. Fahrenheit, Celsius, doesn't really matter, I guess, at those temperatures. The day before, it was 60 below, so we got a balmy day. Well, let's talk about Greenland and Antarctica, because they hold 99% of the world's fresh water trapped in our glaciers. So this is an annual loss of our ice sheets. This is Greenland. We fly satellite data, we fly airplanes, we accumulate all of our data. And it's an engineering display visualization, because I'm looking at the velocity. I'm looking at the velocity vectors, not just how much we're losing in terms of the glaciers, but how quickly we're losing them. Where are we losing them from in 3 dimensions? So we can map, we can monitor. This year we lost 277 gigatons of ice from Greenland. The Arctic is melting even quicker than Antarctic. But we lost another 150 gigatons from the Antarctic ice sheet. So what does that mean? That amount of ice loss is equal to the size of Texas. So it's big. Texas is large. So those are the vital signs. Taking data as a scientist, engineer, we're monitoring and measuring. At the end of the day, it's all about changing human behavior. So I want to show you a little bit more about some of the work we're doing on climate. I call this satellite imagery of the future. I'm going to bring you future images and videos. I have the NOAA, the National Oceanographic Atmospheric Administration model. It's called SLOSH. It's a very detailed model for flooding, very useful, but that is not intuitive. You probably know red is bad, but I don't know, where that is in the world, and it doesn't help me. It doesn't help my family. If I show you this photo of your house, well, you're flooded. But you might say, David, that's a little too late. I can't even get out my front door. So what do? Well, we use Gen AI, and we train on a whole bunch of pre-flood images. Specifically, we look at the Gulf Coast and even Houston, because these are places that the next flood is coming. I can't tell you when, but I know it's coming, and people are in harm's way. So this is what this looks like. A pre-disaster, we look at infrastructure, we look at roads and homes and factories, and then on the bottom, those are generated images of the flood. And I really want to put that in your hand. I want to put that in a hand to give you the information, to make people really understand and have the capability to see into the future. And most importantly, so that policies can be made and we can get people out of harm's way. We also have an energy simulator, an emulator, a simulator. It's open source. It's called En-ROADS. You can jump on the web. It's very fast. It runs on a laptop. It's accessible. We try to educate. We educate a lot of folks, especially go to Washington, to the Hill, to say, hey, you make the energy trades. It has every energy fossil fuel type you want in there. It has solar. It has renewables. It has building technologies. And you're in charge. You're in charge. We want to put you in charge. People are smart. Put people in control. Some people want to decarbonize, some people want to do trees and deforestation. So you can put your hands on all these sliders. Now the disadvantages are that it's inaccurate because it's a global model, and you can't dial in your zip code. What you care about is your family and friends, or Notre Dame, you want to dial in your zip code. So that's what we're working on now. And I know this is busy, but this is the research that's going on. Say if you wanted to think about policies or a carbon tax, we have simulations, that's called En-ROADS that does that. You can also see what are those CO2 emissions that I showed you. They're in the model. We have a very good global models with this, but where's the research going, in the coming years, this year and beyond? We have slow, very large-scale dynamic models. Fine-scale dynamics is even harder. They're not as accurate as we'd like them to be. And we really do want to put it in your hand, go from the global to the local. So what we're doing in research now is we've come up with very fast physics-informed neural nets to address the first challenge there on the large-scale global dynamics. We make them very accurate and trusted AI, trusted machine learning. That's fundamental. It has to be trusted. It has to be repeatable from day one. And we need much more accuracy, again, at the local level. So that's where the research is taking us today, and I literally do want you to put it in your hands. So we call this the pocket climate, what you care about, right? Not everyone in the world has access to a laptop. Matter of fact, the majority of our kids don't around the world, but everyone has access to one of these, a cell phone. So if we can put it in your hands, then we can not just educate and learn, but we can give people a lot of options in terms of what actions they might take. They might take for themselves. It's very dependent about where you live and things that you can do. But that's what we're working on now. Try to get it local, engaging, and make sure that it works for everyone. It has to work for everyone. So the final, I don't know, I think it's kind of a big idea that I want to leave you with is this question about how come Earth didn't get an embassy? Lived in Washington, D.C., and all those beautiful embassies, and every nation got an embassy, and we forgot Spaceship Earth. So how can we rethink that? I want to do it virtually and take every kid in the world, through Earth, through live in the data, educate everybody, and I think we can do it. So that's the idea of this Earth Mission Control. Can we do that virtually? Can we set these up for public schools? Kind of pop up Earth Mission Controls, if centers, if you will. So there's an AI kind of platform behind it, thinking about the operating system. But at the end of the day, it's about people. And when it's about people, it's not about our technology. It's just about engagement. It's about empathy, compassion. It's about having dialogue and trying to, it's all about building the team and the teams of leaders, as we're doing here at Notre Dame, to go into the future to try to get this right. And so that's where our current researchers in some virtual reality, augmented reality, trying to design kind of this Earth, that everyone can see the Earth. We can serve up that data, if you will, but then you get to say what data is most important to you, kind of, I don't know, like Minority Report or something like that, one of those movies, and what dashboards do you want to see, where do you live, and kind of dial that in. And then most importantly, again, is about the people. Get people around the table to share and talk about the data and what it means for them, and their city that they live in. That's all underway, and I want to close then on just a final thought. It really is our choice, and it's our future. Asked you how many saw The Martian. How many saw Hidden Figures or read the book? Yeah, thank you. What a pleasure to be at NASA at the time. Margot wrote an amazing book. She's now writing a book about all the women at NASA. But our African-American computers, our first software engineers, the mathematicians, the ladies who did the orbital mechanics, to get us to the moon, who we didn't know their history. Well, guess what? Hopefully now the world knows her history. It's her story. So honored to meet Katherine Johnson and most of the women who were just fundamental. Now the world knows their history. Just had quite a delight to learn about Sister Aquinas. If you don't know about Sister Aquinas from Notre Dame, the flying nun, since we're celebrating the 150th of engineering here, I had a delightful time looking through the timeline. I didn't know this. I wasn't taught this when I was a student here. But in 1943, Sister Aquinas flew, and she was honored. She didn't just fly. She wasn't just a pilot and flew. She actually got a national medal for both security and peace. And I think that's kind of the epitome of Notre Dame. That's what I learned here. Both, the security, the pride of leading here in the nation, as well as anything we can do for soft diplomacy, for peace. The world, we know, really needs peace. It couldn't be any more important right now. And so I do believe that it's our future, our choice, where we go forward. I love Eleanor Roosevelt's quote here about the future belongs to those who believe in the beauty of the dreams. So it's a call for all students, all learners, to just believe in the beauty of your dreams, and you're surprised what we can do together. And I'll give Pharrell the last word here.
Don't you know that we're able, and that alone makes us major? We can all sit at the table.
So thank you so much for your attention. I think we have time for some Q&A. Appreciate it.
Well, thank you, Dr. Newman, for that incredibly inspiring lecture. So what we've done for the Q&A is we've actually set up microphones on either side of the stage here at the front, because we need to be able to record the questions. So I'm going to invite everybody that would like to ask a question to either queue to the right or the left. We have time for about 5 minutes of questions.
Okay, because there's no questions. I am a professor, so I'll start asking you all questions.
Come on, please. And if you could introduce yourself.
I'm Jack Kornicki, junior aerospace engineer. I was just going to ask, how does the biosuit actually insulate? Because from what we saw, it was like knitted together with fibers. Are they both tight enough to create like a pressure temperature seal, or is there some other method?
Yeah, great question.
employed?
So about the thermal conditioning. So it's really the inner layer, and it's a pressure layer. So the technology and the measurements were just to try to get that third of an atmosphere. So it's really a pressure suit. Now we do measure thermal properties, and in the latest prototype, I know I went pretty quickly over that sleeve, but that latest prototype sleeve, we invented some new materials, actually specifically they're carbon-doped polyethylene. You think of polyethylene, you just think of glass or plastic, but with colleagues and our nanotech friends, it's pretty amazing. We made them into threads, so we could put them through the 3D weaving machine, and so it has incredible thermal properties. And the second part of the answer is the gold lines in the mock-ups that you see there. Those can be, we can do temperature like plus or minus 10 degrees C, like if you're skiing, like heat you up, just make you, a little bit warmer or colder. But you likely know moon is really cold or really hot, plus or minus 200 degrees C. So we're looking at new material development. And that's just what we can do on the pressure layer. I think the real answer in terms of the thermal properties, you're gonna have to wear your overcoat. So you're gonna have a pressure layer. We just decouple that because I still want you to be very mobile. And then we'll need, but basically I'm sure we'll need kind of your overgarment to really address the full thermal coupling. So we do modeling now, and I have like a 42, multi-node thermal model to see how we're going to do that. Still need to develop new materials. We kind of have the modeling down, but now we also have to, come up with the real suit systems that could potentially fly to address that.
Thank you.
So we'll take one more question from this side, and then I think we have one from the other side.
Thank you. My name is Nicholas Schaefer. I'm also a junior aerospace engineer. And my question is that earlier on in your talk, you mentioned the importance of becoming an interplanetary species for the sake of research and development. And later on, you stressed the importance of looking at the climate and solving that issue before it destroys the planet. What do you see as the best way to connect these two together, to share the discoveries and the advantages brought on by both?
Yeah, great question, thanks. So that's why I probably talk about both too. It was when I came back from NASA that I thought I have to, wake up every morning and say, what's the most important thing I can be working on? And climate was it for me. But how we connect it, as an aerospace engineer, we have, we have great training. It's not option B. Sorry, Elon, you're wrong. I know I'm well. It's not, we're going to move people to another planet. There's a reason people aren't in Antarctica. It's cold and dangerous. 1,000 times worse for Mars. I really want to get to Mars because I want to prove, past life, and I'm an explorer, so I'm always looking over the horizon. But you want to come back. You want to come back because everyone you love, your home, your friends, your family are here. So that's how I connect it. It is really space for Earth. We have a whole research group, well, two research groups at the Media Lab, Space Exploration Initiative and Space Enabled. Space Enabled and Professor Wood's work is 100% based on satellite technology and data, but it's all for local communities here on Earth. So that's how I try to bridge and tell that story and say, in inspiration, space and NASA and exploration is one of the most inspiring things. That's why I became an aerospace engineer, maybe you too. And but we have to take that and say, okay, but how is it relevant to people here on Earth, to our taxpayers who are paying the bills, as well as just to everyday life? How does it help someone every day? And then that's how I try to make the connection to climate and lifting up. Like I say, everything we do at the Media Lab is our technologies, but it's all to enhance the human experience. If we're not helping people, it's probably not worth doing.
Thank you very much.
Hi, my name is Jack Kalikak. I'm a senior mechanical engineer. I was curious, kind of similar fashion, are there any specific I know you talked about AI and some of this stuff, but are there any specific technologies that you're looking to solve challenges at the same time in both the mobility aspect and the humanity aspect, and bringing those lessons of mobility specifically into kind of more the satellite imagery and climate?
Yeah, great question, great. So some of the technologies and some of the especially if you're talking about what we can do in space technologies, but like for Earth, what might be so I think a lot about materials, material development. I'm not a materials scientist, but we need breakthrough materials. Again, economically, I think that in space, up on space station or the future, those might be The first, people talk about the new space economy. I study it, guys. But materials and pharmaceuticals are my answer to kind of like materials, and then also some really interesting, new pharmaceuticals, drug development, things like that. It's really wonderful to even be in, close to home, up on space station, just 400 kilometers up, to have that environment to test and look at that. And then I try to, bring them back to Earth and the work, since my work, a lot of it is in biomechanics and mobility. And, but I would share the work of my colleague, Hugh Hare, who's developed the world's best legs. They're robotic legs, so we have superhumans running around, half human, and then the bottom is robotics. And really impactful work, really, really impactful, especially for our vets coming back. Everyone needs mobility. Everyone needs limbs. So we see a future, we don't talk about disability, you accentuate everyone's ability. And again, as technologists, and we have a big role to play, I think, in helping people with that, in that case, daily activities. Again, just that life that they want to lead. And so there's some really amazing work going on with not just prosthetics, but also with all kinds of, if you will, I look at the biosuit in some sense for my Earth applications as just kind of just like a soft exoskeleton.
Thank you.
My name's Jack Quinn. I'm a senior aerospace engineer, and I just wanted to ask, because you talked a lot about like human performance on other planets. What about like the journey getting there, like challenges associated with that?
Oh.
Yeah, as someone who has to drive 10 hours to and from school every time, I can only imagine the difficulties, both mentally and physically, of being in a confined space for months on end.
Exactly. So guess what? Y'all get your astronaut wings, whether you wanted them or not, because we went through that pandemic. And how did you like it? Right? This is what we do to astronauts. This is what I do for a living. We lock up astronauts in isolated, confined environments for like 500 days. Hey, how are you going to do on that Mars mission? So, human factors, health and wellness, the psychosocial implications of being with the team dynamics on this 4-year mission, I can't overstate it. It's so, so important. It's going to be about high performance, but it's also really going to be about people doing well in very, isolated, confined environment, very, very far away from home. And then the second thing I wanted to mention that you kind of alluded to, which I said, the number one showstopper for the Mars mission, for humans, is radiation exposure. We're going to deep space. So that's why we're going to the moon as well. Now that's deep space. We're out of the Van Allen band. So now we have galactic cosmic radiation we have to worry about, as well as solar particle events. And so we have to have radiation shielding. Or there's some crazy ideas about genetics as well. Perhaps we have people who are radiation hard. That's pretty amazing. Any progress we can make, and that's who I want to send. Now we have to work out some policies and laws and things like that. But I want my people to live. I want my people to live and make that 4-year trip. And so all the work that we can do on that is super important here on Earth for cancer. So that's the impact here. Think big. Think about, these crazy Mars missions, but I can't think of, anything, again, that's so important to any progress we can make if it's, relevant. And so radiation comes up as like my number kind of one issue to solve for the human mission to Mars. And like I said, there's really interesting, some of those materials that we've developed, that back to the carbon-doped polyethylene, we actually first did, what did we do? Boron, boron-10, amazing material. So boron-10, materials really offer some potential radiation shielding. Who would have known? Water is really good. So that's a really elegant design solution. You're going to go into a ship, a spacecraft that has water all around the walls because you need to drink it, and it actually serves as really good radiation. So kind of at the systems level of your craft and the people, but then to make sure that we can also do our best to keep our astronauts safe and healthy and well, and bring them back in as good a shape as we can.
Thank you. Oh, and also, what time zone do you use at the South Pole?
What's that? What is it?
What was the time zone that you used?
The time zone in the South Pole, it's I don't know. We just stayed on. I have to say we stayed. I have to remember what it was at McMurdo, like East Coast. It's also really crazy because it's literally the South Pole, right? So where's west, east, and north and south? Like we're going to go study the Western glaciers, but there's really no Western glaciers. So I have to see. I can't remember the time zone. It's a fantastic place to go. I hope you all get to go there and yeah. But it's a most people think I'm crazy, but I think it's one of the most magical places in the world. We need to go.
Thank you.
Thank you.
I think we actually probably only have time for one more question. But after we finished here, there's a reception outside, and David will be available to take more questions then. So let's take the last question here.
Hello, my name is Reagan Ball. I'm a freshman aerospace engineer. And you've been able to do so many amazing things, so I was just wondering if you have any advice for a young woman just starting in STEM.
Yeah, thank you for the question. Well, I'm glad you're a young woman starting in STEM. So I want to say advice, but I'll tell my experience, and this is why I talk about this, and unabashedly, it has to be for all. So you need to see yourself in this, right? And it's not, somebody with glasses on and a white lab coat or something. No, it's you. This is what a rocket scientist looks like, just like you. And so that's really important. So I want to make sure to say that you have to see yourself, and it's more important that you have to belong. So maybe as you go and get some research experience, you're taking your classes and you're studying stuff, they're going to be hard. And we make no apologies for that, because we want to challenge you, because we know how good you are. So the classes are going to be challenging. But I also celebrate failure. So think about that. No one ever told me in my undergraduate career, I'm not comfortable with failure, right? I always ask my students, how comfortable are you with failure? Well, guess what? We're going to practice failing today, because it's really important. I'm an engineer. We get teams together. I fail all the time, right? It's never going to be about your grades. It's just going to be about what you love to do, what inspires you, working with a nice team of folks, learning from them. And so my message to you is, believe in yourself, believe in your dreams, and don't worry about the grades. Just learn whatever you can. That's going to serve you very well. And then I want us all to change the conversation. I always call it STEAMed. I always bring in the arts. I bring in design. We made STEM a thing. And as soon as young people, even younger than you, say, STEM, that's not for me, well, we failed. And I've failed as an engineer if I've made it something else. It's not something else. It's a great education, great way to get a good job, and if your passion is there, I want to make sure everyone knows you don't have to be the best in chemistry or physics. I wasn't. I did okay. So it's no weeding. We were talking about this earlier. It's not weeding anyone out. You're here, you're a freshman, and STEM is for me. Guess what? You're gonna rock it. And all of us as educators need to say, yes, STEM is for you. So we need to open up that no filtering anyone out. It's about filtering everyone in, as far as I'm concerned, and just having that honest conversation that we need everybody, and everyone should be included. And that's how you do great things.
Thank you.
Thank you.
So I just want to bring this to a close by saying to Dr. David Newman, we are so proud that you are a Notre Dame engineering alum, and we could not have picked anybody more inspiring than you to help us bring our 150-year celebration of engineering at Notre Dame to a close. And goodness, there are so many exciting opportunities, exciting challenges, and ways that we can innovate as engineers going forward to ensure that 150 years from now, we look back on another century and a half that we are proud of. So I'm going to present this. I'm going to try not to drop it. This is like I've been concerned about this all day. I'm going to present this to you, Dava, in honor of this lecture and in honor of you. And thank you so much.
Thank you. Here's to the next 150. They want a picture? Thank you. Thank you.